What's up guys, welcome back to the CodeMate. Today we are going to learn one new design data structure topic. Today's topic is on a find median from a given data stream. So we have an input stream and we would like to find a median out of it. It's one of the most frequently asked interview question, and today we are going to explore different ways to solve this problem. Alright, before we proceed, if you are new to the channel, please do subscribe. Alright, now let's get started. So what problem says is you have a given a data stream and we would like to find a median out of it. Now if median is the middle value in the order integer list, if the size of the list is even, there is no middle value. Okay, so the median is the mean of the two median values. So ultimately we would like to find out a median value from the given sorted list. Okay, so you have this stream that is continuously coming up, and we would like to find out at any point of time if we will call a median, then we would like to get the median element from the given list. Now there can be possibility like if there is odd length of your array, then median is directly the middle element of your array list, okay, or array. But if the list having a even length, in this case, then median is going to be whatever the middle element, two middle element, and then you take average of it. Okay, so 2 plus 3 divided by 2, and then 2.5 will be the answer for that. So for as a part of this data structure design, we have to implement two methods. One is to add a number. So you have let's say median class, and then you have a method called addMedian. Alright, and you will pass a number, so it will be added to your whatever the data structure you will use to hold those data, you will add it into that. And then other method is you can call at any point of time that find median, so it will return a median value from the whatever the data you till that point you have accumulated. Okay, so let's say here we have one example where we are calling first time 1, so initially you have only one value, and then again you are calling add 2. So these are the two value we have right now. Find median, so currently it's a even length, so we will return a 1 plus 2 divided by 2, so it will be 1.5. okay, and then again we will add a 3, so now your data having 1, 2 and 3, and again if we will call find median, then we will return. Now because it's a odd length, then in that case we have a correct median element, so we will return that correct median element from the whatever the result you have accumulated. Alright, now let's see how efficient way we can implement this median problem. To implement this two method, let's say one way we can do is in your median class, let's say median is our main class where we want to implement this two methods. Okay, now one way we can do is, let's say to hold this data, whatever the incoming data you have whenever you call this add method, one way we can do is we can, let's say, have array list, or within the list of integer we can store this data whenever you call your add method. Okay, and so that way your you can hold the data. Okay, now how to find a median? So if you see for finding a median, ultimately you want that your whatever the list data list you are holding the data, that needs to be in order. Okay, so ultimately whenever you call a add method or a find median method, at that time you need to do a sorting on this whatever the list you have. So let's say you have this kind of a data input stream, 1, 3, 4, 2, 5. okay, let's say these are the numbers you have in the input. So let's say when you add 1, 3, after adding 1, 3, 4 and 2, let's say this many element I have added, and I'll call a get median. Okay, so at that time the ideal way or the to find a median, this needs to be in ordered. Okay, so ideally it should be in this way, and then you can take this two element and take average of it. So what I'm saying is, either you whenever you add this element, at that time you can call a sorting of those numbers at the same time, or other way you can, whenever you are calling this find median, at that time sort your array and take the median from that. So that way we can achieve this, whatever the two methods that it has been given to us. So in this case, if we would like to calculate the whatever the time complexity it will take, then let's say we took approach whenever we call add, at that time we are going to add that number, and as well as we will also sort that number array. So this list, whenever you call add, at that time you will add it, and then you also do a sorting of that, so that it will preserve the order, whatever the order it comes, or while finding your median, that will be helpful. So during the find median, you just go to the middle of your array and then get the data from that. Okay, so in this case, so whenever every time, let's say we are adding n numbers. Okay, for example, as a n times we are calling this method add number. Okay, and every time you are adding that number and sorting your array list. So ultimately you will need to do this many times you will do a sorting on that. So ultimately your total time complexity it will take is, let's say, n square log n. Okay, if you use a list. Okay, now let's understand what our main requirement, how the data at the end we would like to get, and then how can we reduce this n square to the lower as compared to what we have right now. All right, so this is what the input stream we have. Okay, so in this fashion we are calling a add element to our median array. Okay, and at the end when we call to get a median, this is what the ultimate array we would like to have, because when you have an array in a sorted order, then only we can get the median. All right, so previously, if you see, whenever there is a new add call comes up, we are sorting that array at the same time. Okay, and because of that our time complexity was too high in that case. All right, now in our definition we are always interested to find out a median. In that case we are always interested more to your middle elements. Okay, so whatever these two elements are there, or if there is a odd length, then there is one more element will be there in the middle, and we are more interested to that element only. Okay, so if you see, there will be always one line between this. You have one portion as on the left hand side and other portion on a right hand side. Okay, and whenever if you call a add method to add a new element to your array, so how can we reduce the total time complexity? So for example, let's say I have one more element that is, let's say, call a 2. Okay, so in that case this 2 is going to be, I know that it is going to be come over here. Okay, so in this case I don't need to change any position, or I don't need to touch this element, because it is already in a sorted order. Only thing is I need to just reshuffle elements from your left hand side. So if you see this array, let's say we will remove this element, it is not there. So we have 1 2 3 and 4 5 6. So if you see it clearly, we are interested in this element. Okay, and we can store this whole array instead of in a single array. We can store this in some splitted data structure, and at the same time we are interested to get this element as faster. So how can we do that is, let's say we can use some heap data structure. Okay, and how it will be look like. So let's say here, ultimately from left hand side you will be always interested to have a max element to get in a of one time complexity. Okay, so probably we can have this side as a max heap, we can define as a max heap, and from this side you will be always interested to have a smaller element to come in a of one time complexity. So in this case we can have mean on a right hand side. So ultimately we can have one max and one mean heap, and using that we can have we can create whatever the array list we are using previously, we can store those data in this one. So that way how our overall time complexity got reduced. So probably whenever you are inserting a new element, you will be inserting that element in one of the heap, and then in that case your heapifying will take only log of n. Okay, so let's say if you have n numbers, you will do that for the n log n. So overall previously it was n square, because for each element we were doing a sorting. In this case our heapifying will take all log n, and then you need that for all the elements, so one more n is for that. So ultimately you will have a advantage over there. Okay, now let's understand with a few more example how this max and min heap will be look like. All right, now how we will implement or how we will add data to our min and max heap. So for example, we have this input elements. So these are the elements we would like to add to our median. Okay, so let's say we have one as our max heap, so that is having a all the small element compared to your median. Okay, whatever the there on the left hand side, those all elements will be there in the max heap, and other is your min heap. Okay, which will have a large element, that is a larger as compared to your median. Okay, so let's say one approach we will take is we have this two heaps. Okay, so always we will add elements to our min heap. Okay, and then if that size between your max and min having some variance, then we will move the elements from min to max heap. I mean like from large side to small side. So let's say we have first element 1, so we will add it over here. At that time size of small is 0, so we will not move. So here it will have empty, and this one will have one element. Okay, when 2 comes, we will add 1 and 2 over here. There is a size difference, so we will move 1. We will take min, so it is a min, so we will take min from there and we will add it over here. So now here it will have a 2 and here it will have a 1. Okay, now when we add 4, we will add 4 to your min heap, so on the right hand side, and this is what the our max heap. When you add a 3, so at that time your 3 will be placed at here. Okay, so in this case there is a size variance. So when I say size variance, it will having a size variance of more than length size variance of more than 1. So here it is size having a 1 and here it is 3. So we will do a balance between those two. So we will take one element, we will take a min from this one, add it over here. Okay, so now this 2 is not there, so this one having a 3 and 4. Okay, now again we will do a same thing for this 2 element. So at the end you will have 1 2 3 on this side, and you will have 4 5 and 6 on this side. Okay, so this is what the data you will have in your max heap, and this one here you will have a 4 5 6 in your min heap. Okay, and whenever you need a median, you will take this 2 element and then you will take average of that. And in the case of odd elements, let's say there is one more element is there, then we will always having a size, we will always having a one more element on your min heap, because we are doing a balance whenever your size on your mean side is going having a difference more than 1. So when we add a third element to this array, then only we move one element over this side. So when you have a, let's say one more element, then it is going to be on this side only. So in that case you will take a mean or median from this element. So what I'm saying is, whenever you have a equal size, then take element from both the elements. Otherwise always take an element from your a large element array or mean or from the mean heap itself. Okay, but with this solution there is one problem. So let me take a different array and let's follow the same approach. All right, now let's take now let's see with this example. So these are the elements we would like to add into our median. Okay, so let's say we have, now I'm writing just only small and large. So your left hand side will be all the elements will be small, and right hand side will be all the elements as a large. Ultimately I'm talking about this will be your max and this will be your max and this will be your mean heap. Okay, but instead of that we will write down a small and large. All right, now let's say first we have 1. So 1 we will add first to the large side. Okay, at that time we will not have anything over on this side. Now again we have 5, so that is also we will add on this side. So when we have a 5, okay, so at that time we will add 1 to this side. Okay, so we do not have a 1 anymore, so we will have 5 on this side. Okay, now let's say we have a 6, so 6 we will add on this side. At that time we will not move anything on a small end side, because there is no size difference between these two. only one element size difference, but as we discussed that we always put on a large set. All right, till this time we are good. Now we have 7. Okay, so 7 we will first put on this side. Okay, and there is a size difference, so we'll try to take one element. So we'll take mean from that side and we will add it on a smaller side. So now here we have 6 and 7 on a large side. Here we have 1 and 5 on a small side. Okay, after 7 we have 2, so that we will add on this side 6, 7, and as your 2 is smaller, so it will come at first place. Okay, at this point we will not change anything because only length or size difference is 1. All right, now let's go to the 3. So 3 first we will add on this side. So we have 3, 6 and 7, and we have size difference, so we'll take first or top element from this one, and then we will add it on this side. Okay, and at the same time here we have 3, 6 and 7. Okay, now next to that we have 4. Okay, so 4 we will add on this side. 3, 4, 6 and 7, and at the same time we will not change because there is only one size difference. So this is what we have in the, so this is what we have on the smaller side and larger side. Now if I'll call a get mid, okay, median, then it will give me this element. But if you see, so if you sort or if you see the given input array, then if I'll write it down in the final result, the how it will be look like, then it will be 1, 2, 3, 4, 5, 6 and 7. Okay, so ideally my mid should be this element. Okay, but because of some issue we are getting a mid is equal to 3. And what that issue is, if you see, initially we have larger elements and later we got a smaller element. So what happened was we moved larger element initially on a smaller portion, and those elements never moved back to your larger portion. Okay, so what I'm saying is initially we moved this 5, but that 5 remains over there forever, that never moved to this side. Whenever there was a 3 on this side, ideally your 3 should be on this side and your 5 should be on this side. So let's say that happened, then your final result would be look like in this way. And as your 5 is on this side, so this 4 will come forward, and this is what your ideal result will be look like. Okay, so in this case it will give you the correct result as a 4. So what funda we will follow is, first we will always add element to your large side. Okay, when you add your large side, that will give you the, that will heapify your whatever the data you are adding on a large side, and it will have a correct order, or it will, whatever the element you are adding, that will having a correct position on your right hand side. Okay, after you add your element to the large side, you will also add, you will pull one element from your large. Okay, and you will pull in the sense you will take one element, whatever the top element from this side, you will add that to your small. Okay, okay, and after that, if you see there is a size difference between your small and large, okay, then you will move one element from small to large. In this case you will take the higher, in this case your 5 will move on this side to this side if we follow this approach. So ultimately what we are doing is we are closing the cycle. You add from the large, we will move one element to the small, and again if there is a difference in the size, you will again move one element to the large. So ultimately we are closing this cycle so that whatever this discrepancy was there previously, that will not be there. All right, now let's understand a code for this. All right, so this is what our class median finder, and first we define a small and large heap. So in Java we are defining it as with a priority queue. So our small needs to be in a reverse order, so that is going to be your max heap. So your first element should be max, and then you need to have it in a reverse order. So we have given a comparator which gives in a reverse order, and the second priority queue is in normal order, where your right hand side of the whatever the numbers are there, that will be stored in a large. All right, now let's understand the add method. So add number. So as we discussed, we always add element in the large first, and from large we will take whatever the minimum number from there, and we will try to add it into the small. And at the same time, if we will see if there is a difference between a size, then we will try to move one element from small to large. So at the end, we always want that in the odd condition, if there are number of elements is odd, then that odd number should be present with a large, so that we can pick it up from the large itself. Other way around also we can do, there is no issue with that. All right, so this is what our add method is. Now to find a median, we always will check, because we are putting that in the odd condition, our large will have a higher value. Okay, so if the large elements having a large array having a large heap having a size is higher, then in that case we will always return a value from the large itself. In other case, it means that both the large and small having a same number of elements, and in that case we will take element from both the heap or the priority queue, and then we'll take average out of it and then return it. All right, so that's it in this design session. Hope you guys enjoyed it. Stay tuned for the next design videos. See you in the next video. Till the time, bye bye.